Welcome to this explainer. You know, when most of us hear that an artificial intelligence system can actually improve itself, our minds tend to jump straight to the movies, right? We picture some rogue model rewriting its own code and magically turning into a super intelligence literally overnight. But let's put the sci-fi tropes aside for a minute. The actual reality of AI self-evolution, it's fundamentally a rigorous, structured systems engineering process. There's no magic here, folks. Today, we're going to break down the exact nuts and bolts of how an AI system actually trains itself using controlled iterative loops.
Okay, let's dive into this. Here is our blueprint for today. We're going to start by busting some myths, map out the actual evolution loop, tackle what's known as the control problem, and finally, look at how the entire system, not just the model, evolves safely over time. All right, part one. Myth versus reality. It is definitely time to replace those Hollywood sci-fi tropes with actual systems engineering.
So a lot of people mistakenly believe AI evolution is just this single, monolithic model magically rewriting itself to become super intelligent instantly. But the structured reality is very, very different. Self-evolution is a highly deliberate process, and it's divided across pre-training, post-training, and what we call the surrounding harness. And out of all of these, post-training is absolutely the most effective place to begin. Why? Well, it's pretty simple, actually. Before a model is deployed into the real world, we just don't know exactly where it's going to fail. It's only after the model is working on real tasks that we can observe its true blind spots. Maybe it searches the web really well, but its logic is totally flawed, or maybe it produces confident answers, but completely fails to verify its facts. Post-training is where we can observe these specific failures directly.
Now, what's really interesting here is how we actually fix it post-training. That brings us to section 2, the evolution loop, which happens in 5 distinct stages.
This loop is the absolute core mechanism of how a model actually trains itself. Once weaknesses pop up during deployment, say poor planning, incorrect tool use, or a failure to grasp complex coding problems, the system enters this recursive loop. It starts with diagnosing the weakness. Then it generates targeted data to address it, designs a precise training recipe, retrains the model, and finally verifies the result. Once that's done, the whole cycle just begins again. Let's zoom in on that very first step. Step 1. Diagnosis. The model has to identify exactly where its own performance falls below the required standard. But honestly, this is way harder than it sounds. I mean, an AI might know that it failed a task, but knowing that you failed is very different from understanding exactly why you failed. The system has to accurately isolate the root cause. Did the failure come from missing knowledge? Was it just weak reasoning? Maybe it made a poor tool call or was given a badly designed prompt? Could the failure even come from the external evaluator itself? A truly useful diagnosis has to untangle all these possible causes before any real improvement can even happen.
Okay, so once the system actually identifies a specific weakness, it needs to design new training tasks that target it directly. Simply throwing more data at a model doesn't magically make it better. The system has to generate perfectly targeted data. For instance, if the model struggles with long coding tasks, the system might generate tasks that force it to plan, edit multiple files, and run tests. If the weakness is scientific reasoning, it might whip up tasks around hypothesis generation and simulation. It also has to calibrate the task difficulty, because, easy examples just create a false illusion of progress. It has to figure out exactly how to score the answers and which errors need the strongest adjustments. This highly specific training recipe is absolutely crucial so the model doesn't just reinforce its old mistakes or veer off into new biases.
But, as you might guess, this loop introduces a massive risk. This brings us to section 3, the control problem, and the very real dangers of error propagation inside a closed loop. After the model trains itself using that new data and recipe, we hit a really critical juncture. At this point, the system is no longer just tweaking a prompt, it's actively changing the model's core behavior through retraining. But improvement cannot simply be assumed. So I want you to consider this question. Did the model actually learn the intended skill, or did it merely learn how to satisfy the evaluator? Did it just get really good at beating the benchmark while actually getting worse at real-world tasks? Did it lose performance somewhere else? This right here is exactly why rigorous verification is mandatory at every single stage of the loop. Without that verification, the loop can actually amplify errors instead of capabilities. Just look at this failure chain. A wrong diagnosis produces the wrong data produces the wrong training, and the wrong training produces a model that might actually be worse than it was before. And here is the real danger. The next cycle will then kick off from that distorted starting point. We call this recursive drift. Self-evolution isn't just a training problem, it's a profound control problem.
A tiny mistake early on can spread like wildfire, propagating through the entire loop and distorting the whole system.
So how do we prevent that drift? We have to look beyond the model itself. Section 4, evolving the harness. Because the reality is, the model does not evolve alone. When we talk about self-evolution, people almost always focus entirely on the model. But the model actually operates within an external architecture called the harness. Think of this as the model's environment, sort of like a chef's kitchen. It includes things like prompts, tools, memory, workflows, search procedures, agent coordination, and verification mechanisms. When a model improves, its behavior inside this harness fundamentally changes. A stronger model might not need the same amount of step-by-step handholding anymore. It might use its tools in completely new ways. It might need fewer agents for a simple task, but highly specialized agents for complex ones. Basically, as the model gets stronger, the environment around it has to fundamentally evolve to support it. And this brilliantly illustrates what is really a tightly coupled evolution process. The model and the harness move forward together, kind of like two alternating feet. One step comes from post-training the model. The next step comes from improving the harness. The updated model changes what the optimal harness should look like, and then that new harness creates an environment that changes the model's behavior all over again, revealing new weaknesses and requiring further training. The two literally cannot be separated. Since they move forward together, we need to expand our boundary of what's actually improving here. Let's move to Section 5, the entire system. This brings us to a really foundational concept. Get this. A weaker model operating inside an incredibly strong, well-designed harness can actually outperform a stronger model that's trapped in a poorly designed one. On the flip side, a better model might allow the harness to become simpler, faster, and much more reliable. So, as this quote states, the real unit of improvement is therefore not the model alone. It is the entire system. The real challenge is to improve the model, the data, the training process, the tools, and the workflows all together without letting any single component destabilize the rest of the shebang. Now, pre-training can totally be a part of self-evolution too. A system could, say, improve its own data collection, spot low-quality sources, or strip out duplicates before pre-training even begins. But pre-training is massively expensive, and the feedback cycle is painfully slow. And that is exactly why post-training is the most practical place to build this system. The model already exists, we can observe its failures directly, targeted data can be created on the fly, and the effects of the training can be measured so much more quickly. Let's move to our final section and see how this all builds up. Section 6, sustaining the loop and avoiding the dangerous traps of self-evaluation. Even in post-training, self-evolution is incredibly tricky, mainly because a system can easily get trapped by its own evaluations. If it only ever generates its own data and uses the exact same judge to evaluate every single cycle, well, its diversity shrinks. It basically gets trapped in an echo chamber. To keep this running reliably long-term, we need strict engineering conditions. You absolutely need independent evaluation. You have to preserve external evidence to anchor the system to actual truth. You need rigorous regression testing just to make sure old skills aren't being forgotten. You need diverse training environments. And crucially, you need stop and rollback mechanisms. The system has to remember not just what it improved, but what it might have sacrificed along the way. This sets up a stark contrast between weak and strong self-evolution. Weak self-evolution simply says, repeat the loop. But here's the thing, a system that repeatedly improves the wrong objective doesn't actually become more intelligent in any useful way. It simply becomes more efficient at being wrong. Strong self-evolution, on the other hand, is about improving the entire system without losing truth, stability, or control across all different contexts. So what does this all mean? The central takeaway is that AI self-evolution is a controlled loop of diagnosing, generating data, training, and verifying, all happening alongside an evolving harness. But remember, the loop is only as reliable as its verification. Just completing one single loop, that's not the actual achievement here. Safely sustaining the system over time is the real victory. Which leaves us with a critical, somewhat provocative question to ponder. Are we truly prepared for the real challenge of sustaining many evolution loops without hidden regression or recursive drift? Thank you so much for joining us for this explainer, and I hope it brought some clarity to a seriously complex topic.